Coherent communication with waveforms, presented by Meenakshi Sharma, Sonal Jawan, Ankit Pandey, guided by Dr. Saurabh Mehta. First, we look at the prerequisites, that is, the performance degradation factors. There are three major performance degradation factors, which is ISI, electrical interference, and thermal noise. ISI, electrical interference, their effect can be mediated by using devices like equalizers at the receiver side. Thermal noise. First, we study about the white noise. Why the word white is used here? Take the example of basic color spectrum having red, blue, green color. When mixed in equal proportion, they produce a white color. Similar is the case with the white noise, where all the noise components are present in equal proportion. White noise has a uniform power spectral density throughout the entire frequency range. As shown below in the figure, figure A is the power spectral density of the white noise, while B is the autocorrelation function of the white. Thermal noise is due to the random motion of electrons. Thermal noise is unavoidable, and thus we have to design a system that takes into account a thermal noise. Now we will study about the demodulation and detection. This is a basic block diagram. Si of t is the transmitted signal, where S1 of t stands for binary 1, S2 of t stands for binary 0, RT is the received signal, NT is the noise. Figure which was shown before highlighted two steps in the demodulation detection process. Step 1, the waveform to sample transformation. It is made up of demodulator followed by a sampler. At the end of each symbol duration t, the output of the sampler, the pre-detection point, yield a sample Zt, sometimes called the test statistics. Zt has a voltage value directly proportional to the energy of the received symbol and inversely proportional to the noise. In step 2, a decision detection is made regarding the digital meaning of that sample. We assume that the input noise is Gaussian random process and that the receiver filter in the demodulator is linear. A linear operation performed on Gaussian random process will produce second Gaussian random process. Thus, the filter output noise is Gaussian. The output of step 1 yields the test statistics Zt is equal to Ai of t plus No of t, where I is equal to 1 of 2, representing binary 1 and binary 0. Now we will consider about the SNR and digital communication. When it comes to the analog communication, the power signals have average power which is finite, energy infinite. Therefore, in SNR for digital communication, we use EV by NO, which is the bit energy divided by the noise power. It is related to SNR by the formula shown on the right hand side, where EV upon NO is equal to S by N into W by R, W being the bandwidth, R being the bit rate. For energy signal, the average power is 0 and energy is finite. Detection of binary signal in Gaussian noise. We will study about maximum likelihood detector, matched filter, then how performance is optimized by using matched filter, and error probability performance. For maximum likelihood detector, the green region denotes the error when message 1 is transmitted and 2 is detected. The right hand side of the graph shows the likelihood of S1, that is when probability when S1 is transmitted, Z is detected, and the left hand side the likelihood of S2, that is the probability when S2 is transmitted and Z is selected. Two hypotheses H1 and H2 are used here. Hypothesis H1 stands that Zt, the detected part, is greater than the gamma, the threshold value. Then hypothesis 1, that symbol 1 was transmitted, and similarly vice versa. Now we will talk about the maximum likelihood receiver. A popular criteria for choosing the threshold level gamma for the binary decision is based on minimizing the probability of error. The computation for the minimum error value of gamma is equal to gamma naught starts with forming an inequality expression between the ratio of the conditional probability density function and the signal a priori probabilities. Since the conditional density function is also called the likelihood of S1, the formulation given below in equation 3.3 3, 1, where P S2 stands for probability of S2 being transmitted, P S1 stands for probability of S1 being transmitted. This is also known as the likelihood ratio test. In this inequality, probability that S1 and probability that S2 are transmitted are a priori probabilities, that is prior to the detection. H1, H2 are hypotheses as explained before. To minimize the error, we should choose a hypothesis H1 if the ratio of likelihood is greater than the ratio of a priori probabilities as shown in the equation 3.31. If both the probabilities are equal, we get a gamma naught, or the optimum value, which is mean of A1 and A2. This is the optimum threshold for minimizing the probability of making an incorrect decision for the important special case. This strategy is known as the minimum error. For equally likely signals, the optimum threshold gamma naught passes through the intersection of likelihood functions as shown in the figure above. Thus, by following the equation, the decision stage effectively selects the hypothesis that corresponds to the signal with maximum likelihood. For example, given an arbitrary detector, the output value ZAT, for which there is a non-zero likelihood that ZAT belongs to either class signals of S1T or S2T, one can think of likelihood test as a comparison of the likelihood values. The signal corresponding to the maximum PDF is chosen as the most likely to have been transmitted. In other words, the detector chooses S1 of T if probability that when S1 was transmitted, ZA was detected is greater than probability that when S2 is transmitted, ZA is detected. Otherwise, the detector chooses S2. A detector that minimizes the error probability is also known as maximum likelihood detector. QX is called as the complementary error function or co-error function, and it is commonly used symbol for probability under the tail of the Gaussian PDF, which is usually an error region. It is defined as Q of x is equal to 1 upon 2 pi integration from the limits of x to infinity p raised to the power of minus u square upon 2 du. On approximation, it yields 1 upon x under root 2 pi e raised to minus x squared upon 2. Matched filter is designed to provide maximum SNR. The received signal is matched with the filter response at sampling instance, and thus matching of signal takes place. Noise is reduced and SNR is increased. In terms of optimization, the gain region or the error region is reduced, and thus match filter is an optimizing technique to reduce the error. What is colored noise? When the power spectral density of noise is not uniform across the entire frequency spectrum, it is called colored noise. There exist non-zero values of autocorrelation or autocovariance at different time instants for the colored noise. The autocovariance is maximum for zero lag, L is equal to 0, and decreases gradually from increasing and decreasing values of Gaussian noise has two types, colored noise and white. We have now receiver structure for detection of colored noise, which is divided into two parts. One is signal demodulator to convert the received waveform RT into n-dimensional vector. The detector is to decide which of the n possible signal waveforms was transmitted based on observation of the detector. There are three methods of detecting signals in colored Gaussian noise are sampling approach, the Coulomb expansion, and whitening approach. The sampling approach. Sampling approach has a received signal with the Gaussian noise and decision making. Here we use the receiver, map receiver, maximum a posteriori receiver, and the decision making is done on the basis of maximum likelihood condition. Next is the Coulomb KL expansion. Here we introduce eigenvalues and eigenfunctions to convert the noise, colored noise, into scalar entity so that we can easily eliminate that noise at the receiver. It is whitening approach. In whitening approach, we rederive the receiver by imposing a whitening filter upfront. That is first whitening filter and then deceiver algorithm. Whitening approach has two types: infinite observation interval and finite observation. In infinite observation interval of whitening approach, we have two parts, that is first whitening filter and then matched filter. In whitening approach of finite observation interval, we have only one filter, which is used as combination of whitening and matched filter. Thank you.
Quadrature-Amplitude Modulation and Demodulation. Introduction. The QM modulator and QM demodulator are the key elements in any quadrature-amplitude modulation system. The modulator are used to encode the signal on the radio frequency carrier that is to be transmitted. The demodulator is used at the remote end to extract the signal from the RF carrier so that it can be used at the remote end. The QM is widely used for modulating data signal onto a carrier for a radio communication, and it is widely used because it offers advantage over other form of data modulation such as PSK. There are basically two types of quadrature amplitude modulation. One is analog QAM and other is the digital QAM. Now we will start with the analog QAM. The analog QAM allows multiple analog signal to be carried on a signal carrier, and it is basically used in the PAL and NTSC in television system. Digital QAM. What is digital QAM? Digital QAM is used for digital transmission for radio communication application. It carries higher data rates than ordinary amplitude modulated scheme and phase modulated schemes. Now we will see what is the quadrature amplitude modulator. Here the block diagram, this is shown in the figure as the in the QAM, the original information, that is we say the input signal, is split into the two parts that consist of odd signal IT and even signal QT. The odd symbol is applied to the upper multiplier and the other input to the other is applied to the input to the multiplier coming from the local oscillator. The output that is produced by the first multiplier is given by summation of minus infinity to infinity a suffix k p1 t minus kt, whereas the signal from the coming from the even multiplier is by the, that is the output given by the second multiplier, that is even signal, is qt is equal to summation of minus infinity to infinity b suffix of k p1 t plus kt. The output from both the multiplier are then applied to the respective low pass filter, which removes the noise that is present in both the signal. The signal coming from both the multipliers are added together by the adder and given for the mathematical operation. Thus, after performing the mathematical operation and by adding the two signals, the output signal, that final signal, we get as a transmitted signal, which is given by under root of p into I of t cos omega ct minus qt sin omega ct. Here p represents the transmitted signal power, it is in phase, qt is the quadrature baseband, and omega c is the carrier frequency. Now, thus we have seen the modulator of quadrature amplitude modulation. Now we will see the what is demodulation process of QAM. Here there is a similar process like what we have seen. There are the two inputs in the demodulator process also, which at the receiver side the transmitted signal is r of t under root p I of t cos omega ct plus theta minus qt sin omega ct plus theta, and here noise is added along with this signal, that is n of t. The output from the first multiplier is given by r1 of t, which is given as under root 2 cos omega ct plus theta. The output coming from the second multiplier, that is from the even signal, is minus under root 2 cos omega ct plus theta. Here theta is a random carrier phase, and the output of first input and the second input after removing the noise comes as r of t or I of t with respect to local pass filter with respect to low pass filter under root p by 2 I of t, r of t, r q t with respect to low pass filter is equal to under root p by 2 q t. Here now we will see the bandwidth of a quadrature-amplitude modulation system. Here the frequency of bandwidth is 2fs and the power spectral density is shown over here, and this side is the main lobe. The bandwidth is given by fs minus of minus fs, that is we get 2fs, where fs is equal to 1 upon ts. Okay, so this substitute at the place of fs, then we get as is equal to 2 upon ntb. Here ts is equal to ntb. We substitute ntb on the place of ts, thus we get the bandwidth as 2fv upon capital N. Here now we see what are the types of QM. The types of QM, depending upon the number of bits per message, the QM signals are classified as below. For QM, the bit per symbol will be 2 and number of symbol will be 4. For 8 QM, the bit per symbol will be 3 and number of symbol will be 8. As it goes on, and at the last 64 QM is given as a bit per symbol is 6 and the number of symbol is equal to 64. Here among them that we have explained the types of QM, among them 8 QM is given, is shown in the figure. It is a QM transmitter. In this the 3 inputs are given, and which again goes to a 2 to 4 level converter on both the side, that is on the odd side, odd channel, and the even channel. And this is given to the product modulator, which modulates the signal. Other inputs to the product modulator is coming from the reference oscillator, which is added, and the input signal that is coming to the reference oscillator in the events channel is phase shifted by 90 degree, and these signal are then after product modulator they are given to the linear summer, which is used for the summation purpose, and then from there, after summing this signal, these are given to the band pass filter, which removes the noise, which selects the particular bands as per the need and passes the output as a 8 QM output. The truth table is shown in the figure B for the 3 inputs. Here as we can see in the first diagram shows the truth table, second is a phasor diagram, and third is a constellation diagram. Here the error probability performance. This is the error probability performance is with the probability with respect to, it is a graph of probability error performance with respect to E by N0 in dB. Here as we can see that for psi 0 we get the value as infinity. As it goes on changing the value of psi we get as rho psi is equal to 16 and rho psi 14. As when we keep the rho psi value as a 12, then we see that the difference between the rho psi is equal to infinity to rho psi is equal to 12, there is almost a difference of 2. So the error probability will be better at rho psi is equal to infinity. Now we see the advantage. What is the advantage of QM? It transmits more bits of information per symbol. It provides good scope of high bit rate by using higher order of QM, and it is more efficient technique as compared to CPM. It is best technique to be used in a linear region of operation. What is the disadvantage of QM? It is more susceptible to noise. It requires coherent demodulation with exact phase and frequency. The last one is QM is totally based on linearity concept, that is linear amplifier and receiver, and these linear amplifier are less efficient and consumes more power. Application: it is used in Wi-Fi, it is used in the cable modem, and it is used in the digital video broadcasting, it is used in the WiMAX. These are the practical application of QAM.
Bibliography 1. Digital Communications, Fundamentals and Applications, 2nd edition by Dr. Bernard Scala. 2. Digital Communication Techniques, Signal Design and Detection by Marvin K. Simon. 3. Digital Communication Techniques, Signal Design and Detection by Simon Haken. 4. www.khanacademy.com for statistical concepts. 5. www.wikipedia.com for general information. Thank you.